In this video, I will talk about how to do indefinite integration by substitution. Previously, we have learned some standard integration formulas, but they cannot handle situations like this. Now I'm going to show you the standard procedure of doing this integration by substitution, and afterwards I will explain to you why it works. First of all, we can do a substitution to let u be 3x minus 1. And then we can differentiate u with respect to x, and therefore we can get that du dx is equal to 3. Furthermore, we can manipulate this as if it is a fraction, and then we can get that dx is equal to 1/3 du. Later on I will explain to you why we can do this. Now we can rewrite two parts in this indefinite integral. First of all, we can rewrite 3x minus 1 to the power half to be u to the power half. And then we can rewrite dx to be 1/3 du. Afterwards, we can do integration as usual, and we can get that the result is equal to 2/9 times u to the power 3/2 plus c. Please note that it is not yet the final answer, because we should substitute this back into u, so that the result is in terms of x. This is the standard procedure of doing this kind of integration. Now the question is why we can do this. We have learned that a derivative is just a limit, but not really a fraction. If that's not a fraction, then doing this will be meaningless. That means now we want to know whether this kind of transformation is correct. And to verify this, we can try to differentiate this and see whether the result is this integrand. If the result is this integrand, that means this kind of transformation is correct. To differentiate this indefinite integral, because this indefinite integral is with respect to u, so we should apply the chain rule like this. By differentiating this with respect to u, we can get back the integrand, and then du dx is simply equal to 3. Now we can see that this 3 and this 1/3 can be cancelled. This is not a coincidence, because this 3 comes from du dx, and this 1/3 also comes from du dx. And because u is equal to 3x minus 1, therefore the result is 3x minus 1 to the power half, and it is exactly the integrand. Now we can see that we can really do this, and the reason behind is that the chain rule is correct. In other words, when we are doing the integration by substitution by following this procedure, we are essentially reversing the chain rule. On the other hand, if we can do this kind of manipulations for differentials, then we can come up with some properties of differentials. The first property states that we can take out any constant factor inside a differential. And it is true because we know that dkx over dx is equal to k, and therefore dkx is equal to k dx. The second property states that any constant added inside a differential will not affect the differential itself. It is true because we know that dx plus c over dx is equal to 1, and therefore dx plus c is equal to dx. The third property is the general case, and it is the most useful one. It states that dgx is equal to g prime x dx. It is true because we know that dgx over dx is equal to g prime x, therefore we can have this result. By knowing these properties of differentials, we can try to do this integration again without letting u. First of all, we can multiply 3 inside the differential so that it will match the 3x here. According to this property, d3x is equal to 3 dx, so we should divide 3 here so that we can end up with doing nothing. Afterwards, we can subtract 1 inside the differential so that these two can match. And according to this property, subtracting a constant inside a differential will not affect the differential, therefore it is alright. Now because the variables are the same, we can do integration as usual, and we can get the same result as before. These two methods seem different, but they are actually equivalent. That means they are doing exactly the same thing, and it is reversing the chain rule. Now let's take a look at some more examples to understand the integration by substitution better. In the first example, to integrate this, we can first of all let u be x squared plus 2. so that du dx is equal to 2x, and then we can make dx the subject of the formula, so that dx is equal to 1 over 2x times du. Now we can do substitution by rewriting this as u to the power 100, and we can rewrite dx as this, and we can see that the x can be cancelled. Therefore, the integral is equal to this. Now we can do integration as usual, and we should substitute this back into u so that we can get that the result is equal to this. On the other hand, we can also do this integration by manipulating the differential. First of all, we can put this x inside the differential. To do this, we should refer to this property. We should apply this property from this side to this side. That means we want to put this inside the differential. To find gx from g prime x, it is the concept of integration. We want to find a primitive function of this. That means now when we want to put x inside dx, we need to integrate x so that we can get 1 over 2 times x squared, and it is inside the differential. And then according to this property, this half can be taken out. And then according to this property, we can add 2 inside the differential. Now the variables are the same, and we can do integration as usual. Next, let's take a look at this example. In the second example, to integrate this, we can first of all let u be this, so that we can get that du dx is equal to 4x cubed, and hence dx is equal to 1 over 4x cubed times du. Now we can do substitution as usual, and then we can see that this x cubed can be cancelled. Afterwards, we can do integration as usual, and it should be equal to 1 over 4 times natural log of the absolute value of u plus c. When we substitute 1 plus x to the power 4 back into u, we can remove the absolute value, because 1 plus x to the power 4 is always greater than 0. Therefore, this absolute value sign is meaningless. Similarly, we can also do this integration by manipulating the differential. We can first of all put this x cubed inside the differential by integrating this x cubed, so that we can get 1 over 4 times x to the power 4. Afterwards, we can take out this 1 over 4 and then add 1 inside the differential, so that we can do the integration as usual. Next, let's take a look at example 3. In this example, to integrate this, we can let u be x to the power 3, so that du dx is equal to 3x squared, and then dx is equal to 1 over 3x squared times du. Now we can do substitution as usual, and we can see that this x squared can be cancelled. Afterwards, we can integrate this and then substitute this back into u. Therefore, the final result is this. On the other hand, we can also do this integration by manipulating the differential. We can put this x squared inside the differential by integrating x squared, so that we can get this. And now we can take out this 1/3. And then we both have x cubed here, therefore we can do integration as usual. Next, let's take a look at example 4. To integrate this, we can first of all let u be log x, so that du dx is equal to 1 over x, and dx is equal to x du. Now we can do substitution, and we can see that this x can be cancelled. Therefore, now we can do integration straightforwardly, and we can substitute this back into u, so that the final result is this. The other way to integrate this is first of all putting this 1 over x inside the differential by integrating 1 over x, so that we can get this. Normally, we should put the absolute value sign here, because integrating 1 over x will give us a primitive function of log absolute value of x. However, in this case, there is no need to put the absolute value sign here, because from the integrand, we can see that the domain of the integration is all positive x. Therefore, we can rule out the cases of negative x, and therefore the absolute value sign is meaningless. After this, we can do the integration straightforwardly. Next, let's take a look at example 5. We have already learned how to integrate e to the power x, but when the base of the exponential function is not e, we should consider substitution, like this. We can let u be 5 to the power x, so that we can get that du dx is equal to 5 to the power x times natural log of 5. And then we can get that dx is equal to 1 over 5 to the power x log 5 times du. Now we can do substitution like this. Now the problem looks more complicated, but actually it is not, because u is exactly equal to 5 to the power x, therefore they can be cancelled, and as a result the integral is equal to this. Integrate du is equal to u plus c, therefore the final result is equal to this. In this example, if we want to integrate this without letting u, we should first of all express this exponential function in terms of base e. By the property of logarithm, log 5 to the power x is equal to x times log 5. Now in order to match these variables, we should multiply log 5 inside the differential, and then at the same time we should divide log 5. Now the variables are the same and we can do the integration like this. In addition, we should reversely express this as 5 to the power x. Finally, let's take a look at example 6. This example is a little bit different from the previous examples, and we shall see. In this integration, we can let u be x plus 6, so that du dx is equal to 1 and dx is simply equal to du. After doing substitution, we can see that the integral becomes something like this. This x cannot be cancelled, and we cannot do further integration. In this case, we should also express x in terms of u by making x the subject of this formula, and we can get that x is equal to u minus 6. So what's the point of doing this substitution if nothing can be cancelled? The point of doing this is that now the integrand can be expanded. Originally, the integrand cannot be expanded, but now we can do expansion after substitution, and then we can do integration as usual. Therefore, the final result is equal to this. From these examples, we can see that integration by substitution may not be easy. Sometimes it may require some experience to figure out a workable substitution. For the same integration problem, there can be more than one workable substitution. Generally speaking, there are two major purposes of doing substitution in integration. The first purpose is to do cancellation, and the second purpose is to do expansion.